Unsiloed podcast is produced by University FM, elevating the stories of your institution.
Welcome to Unsiloed. This is Greg LeBlanc. I'm here today with Joe Boaler, who is a professor of mathematics education at Stanford University, and also the author of a number of books, including Mathematical Mindset. I think there's one called Elephant in the Classroom from way back, and then Limitless Mind. And the most recent book is called Mathish. Mathish, new word, Finding Creativity, Diversity, and Meaning in Mathematics. Welcome, Joe.
Thank you. Thank you for having me.
You know, when I read this book and your other work, for someone who's been teaching for a long time and learning for a long time, but having never been, I guess, exposed to, I don't know, education and how to teach math, having been teaching math, it seems like everything you say makes perfect sense to me. Right? And so I don't understand why you have to write what you've written. So, um, your main message is that not only is math being taught incorrectly or taught in a way that's less productive than it could be, but also that we emphasize the wrong subject matter in our education of students, particularly at the high school level. And I've been making similar points. I teach sort of a boot camp for incoming MBA students where I try to just teach them what it means to do quantitative reasoning and problem solving. And it kind of leans on a lot of these things before I even was exposed to your ideas. So I guess the first question I would have for you is, why on earth is this work so necessary, right? I mean, it seems like, common sense in a way for people who have actually been trying to teach for things like math.
Why is it so necessary? Well, as you alluded to earlier, to not happening in schools. And the problem with mathematics education in schools, it's not the fault of teachers, but somebody's decided all of this content needs to be taught, and they've listed it as hundreds of standards. And textbook authors have taken those standards of little bitty statements of procedure and turned them into procedural questions. And that's what's used in classrooms. So students don't get really interesting mathematics. They don't get even the maths they need for the world. But when you try and change that system, it's really hard.
Well, you pointed out math literacy is something that is, I mean, I don't think we can say that it's on the decline, but it's certainly not where it could be. And of course, in today's world, it's increasingly important that we have some math literacy and data literacy. And so you point to these three flaws in the current educational process, right? The over-tested subject, the misrepresentation of math as being a set of procedures, and this notion of the intrinsic math brain. And it seems like these dogmas have developed over time. Has it developed mainly because when it comes to teaching, I don't know, there's a certain logic to teaching that is all about testing, which has effectively needed some kind of, I don't know, theory behind it?
Hmm. It's a little hard to know exactly why we're in the state we're in right now. I mean, arithmetic was first taught in schools because people needed it to work in shops and to work in industry, and they needed to be able to add and count, and we've never changed from that system. I mean, the mathematics that's taught in schools in the US was set out in the 1800s, if you can believe that, and has not been changed since then. So, of course, the world has changed. What mathematics we need has changed. But when people try and make change, they get huge pushback from people who say, no, I just want maths to stay the way it's always been.
Well, it's interesting because I think you say in the book that the people who have been super successful under the existing regime are the ones that are most resistant to changing it. But when you look at how those people actually do math, it seems to be much more in alignment with what you think we should
That's
be
actually
teaching.
right. That's a good point. The way they're using maths in their own lives is basically what we're saying kids need. But I think there's sort of deeper reasons why some people try and block change. from a system that's been in place for a long time. I was recently reading a political scientist book on this. It was very interesting. She's mapped educational change in different countries and over different decades around the world. And she notes that whenever people try and change school systems to be more equitable, the elite in society block it. And this is what we've seen. This was how people tried, the people who tried to stop California maths framework. It was solely one group of people, the very, very successful elite. And so this does seem to be a pattern that plays out over and over.
Right. So in other words, if you have a process that creates someone that is, I guess, optimized for that particular system, they want people like themselves to
Well, and they know how
continue.
to work that system. They know how to work it for their own children. So here we are in a situation where maths has barely changed over many years.
Well, maybe we can talk about how you became an educator of educators, because at one point you were a lowly math teacher, right? Actually grappling with teaching kids math. How did you get from that to becoming a professor of math education?
Good question. Well, I at first was a maths teacher in London, which I'm from England, and when I was in my teacher training year, which I did at London University, that was when I was first introduced to a different way of teaching maths. And then I went into teaching in London, and just early on in teaching, I decided to do a master's degree because I was really interested in how we think and learn and teach. And then I did a PhD at London University, and I was presenting the results of it one day at a conference in Athens in Greece, and Stanford had a search for a maths education professor, and some of the Stanford professors were in the audience, and they just came to me and said, "Do you want to come to Stanford?" And I said, "No, not really." And I went back to London. They started sending me picture books of California and saying, "Just come for a visit." So I ended up flying to California to see it, and then I stayed. So that's how I moved into being a professor. And I love to teach, so I never really wanted to leave teaching. But of course, as you know, we teach as professors. So I teach undergrads at Stanford, and I teach teachers, people who are training to be teachers. So I still get my teaching in.
Well, I mean, a lot of what you're doing is you are doing what we might think of as, I don't know, RCTs on teaching effectiveness, right? And it does seem kind of odd that we have not done a lot of these types of A/B tests. And one of the earliest podcasts I did was with Dan Willingham, and of course he is an expert on reading and the teaching of reading. And I asked the same question to him, right? Why isn't that? I mean, we do experiments to validate the efficacy of various medical procedures, pharmaceuticals, medical devices, and so forth. And, you could argue that medicine is important, but education is something that everybody has to go through, whereas medicine might be something that, only sick people have to deal with, right? So why haven't we been doing sort of
Well,
RCTs
we
on?
have. There are quite a lot of RCTs done. It's always rather complex in education, though. First of all, it's not very appealing to the districts and the schools involved to enter an experiment where half their kids get something good and the other half don't. So you're already up against trying to get that kind of experiment done in schools. But even when you do the experiments, there are so many variables at work in schools, so many differences. You can try and contrast two things, but of course, there's all these other things that come into it. So it's not as easy to do a sort of controlled experiment in a complex human environment with different teachers and different students and all that they bring. But some people have done it. There are RCTs in education, and I was reading a really interesting one recently. I think I quote it in Mathish, where they had different teaching approaches in the introductory college years, and so they found very clearly with experimental evidence that active learning of undergrads was more successful than sitting, listening to lectures. And that was a pretty strong RCT. They managed to run lots of different sections of different undergrads. But you're right, there's not a lot of them in education, particularly in K-12 schools.
Now, I think the key features that you're emphasizing are active learning versus passive learning. You emphasize, I think, visual. There's a huge visual emphasis on the visual understanding of content,
Yeah,
and then there's this emphasis on metacognition, right? So understanding how one learns while one is learning, and I think this has applications, of course, outside of math and to
absolutely.
other
Yeah,
parts of education. So I was
and
wondering
to
if you could start by
industry.
just telling us a bit about metacognition and how important it is and how we can teach it, right? How do we teach
Yeah,
people to be more conscious of how they're thinking and
yeah,
learning?
no, great question. I know a lot of people think of metacognition as thinking about your own thinking, and that is a piece of it. But people who are metacognitive have a whole different way of being in the world. And one is when they're asked to work on something, they think of different strategies and they can choose between different strategies. They're more likely to ask, why does that work? And think a little bit more deeply about the processes. So there's a whole sort of portrait of a metacognitive person that is more actively thinking about the knowledge, aware of their own learning, but also different ways to approach content, different ways to approach tasks. So we can absolutely teach that to people. And I was watching a video today, actually, of one of the teachers who I think is best at doing this. And what I communicate to teachers is it's really teaching kids how to learn. And if anybody who teaches maths should assume that when kids come to them, they've developed unproductive ideas about maths, because that's what's out there in the culture and that's what's in most schools. And you have to teach them how to learn successfully. I actually have my undergraduate class at Stanford is called How to Learn Maths. And it's always oversubscribed, and the students are always mind blown when they find there's a different way and different maths. And but yeah, you could definitely teach that to kids. But most teachers don't. They start their maths class from day one, just giving kids maths questions and expecting them to do them. And they don't think about the process of what is involved in actually approaching a question well. That's not really part of a teacher's thought processes normally. So yeah, you could teach people to be metacognitive, and those are the people that are more successful, not just in maths tests, but in life, in work, in many fields.
So, I mean, is it harder to teach that? I mean, I went to Montessori school, and so everything you spoke about made perfect sense to me. I learned how to learn, you know, as early as I started learning, right, just from day one. And so when I went to a more mainstream educational system, I was just really disappointed in what the teachers were doing. But it didn't seem like my teachers in the Montessori school, had to work any harder. I mean, if in some sense it seemed easier. I mean, for them,
Well,
right?
I don't know if it's easier, but it's nicer. When we teach teachers to teach in this way, they come back saying, oh my gosh, it was so much better. The kids are really engaged. And of course, then it does become easier if your kids are engaged and interested. But most teachers have never had any exposure to that kind of teaching. And they haven't learned to teach in those ways. They didn't go to Montessori schools themselves. If they did, they're probably way ahead. And so they went to private public education. They experienced maths as a series of procedures themselves. Then they just go into the school system and teach as they learned.
Well, is a lot of it due to the pressure to do continual evaluations, right? I mean, the teachers have to sort the students and evaluate the students and grade the students, and so the students feel like they don't have time to do any kind of metacognition.
I mean, the teachers that I work with will often say, I love this. They'll see videos of students really engaged. And they'll say, I love, this idea of going into depth on tasks and asking questions, but I don't have time. I have to get through all these textbook pages to prepare for the next test. And they're really stuck. They really don't feel. Now, there are teachers, and they tend to be more experienced teachers, who've taken the leap and said, okay, I'm going to use these richer tasks. I'm going to spend the time. And what they find is their kids' test scores go up. But for less experienced teachers, they're afraid to take that leap. They think they have to just go through every page of the textbook, and it's so uninspiring for kids.
Yeah, I think you mentioned that they are trying to do too much, right? So, the breadth of material is too big, right? And they should try to do maybe fewer things, but do them better.
Definitely, which is what happens in other countries. In the US, we have this system of teaching everything every year. So, you start learning fractions in maybe grade 3, but you also learn them again in grade 4 and grade 5 and grade 6. And at the end of that, kids don't understand fractions. And everything is taught every year. Whereas if you look at very successful countries like Japan, they don't teach in that way. Fractions is taught in 1 year group, deeply, well, conceptually. So this is why you see kids going around with these massive textbooks that they can hardly carry, because it has all this content. And of course, when you try and teach everything every year, often kids don't learn any of it well.
Hmm. Well, you reference this concept of compression, right? Which is, you learn something and then you consolidate it, and you then have the capacity to reference it, as long as it's stored in the right way,
Yeah,
right?
right. There's really interesting work that says when we learn maths, we go through this process of compression in the brain. So as a young child, when you first encounter addition, say, it takes up literally a big space in the brain, and a big literal space where the brain is figuring out what this is, where it goes. But over the years, as you get older, that knowledge of addition gets compressed into a smaller and smaller space. So as an adult, if we're given a question like 3 + 5, we can just pull all that out of our mind and use addition. But it is a process called compression, but you only compress ideas. It's not, when you teach kids just method after method after method, they're not even engaging in compression. And it just seems like it's a never-ending list of disconnected topics.
Right. So people are taught to memorize things like
Yeah,
these procedures.
memorize the procedures.
I never heard this quote, but you said that this is a common phrase in math education, right? Ours is not the reason
Oh, yeah.
why, just to,
The flip and multiply.
flip and multiply,
Yeah,
right? I'd never heard that before, but oh my gosh, I feel sorry for students that are taught in that way, right? They're discouraged from, asking the why,
right.
right? Why does this work?
Why does
How does
this
this
work?
work?
Really important question. And, when we ask kids to reason about maths and to come up with their own conjectures, we like to share that word with kids. This is a word that all mathematicians use, a conjecture for an idea they have that you need to test out, like a hypothesis in science. But kids have never heard of that word, which is, means there's a reason for that. But anyway, we teach our kids to come up with conjectures and then to reason about them and prove it to each other. And they get these great discussions where they're reasoning and being skeptical with each other. And that's what sparks their interest. They actually feel like they're discovering new things. And it's like really engaging for the kids to get into these discussions about the meaning of why these things work in maths. So it's a great route not only to engage kids, but have them understand what they're doing. But yeah, it's not that common.
Well, the other thing you emphasize is the social nature of learning, right? And so, when I would teach my boot camp to the MBAs, I would do these in-class exercises, and I would say, turn to the person to your left and work on this stuff together, right? And if one person has an insight, share it
Right.
and go back and forth. And
Right.
this seems very different from, I have a nephew that goes to the Lycée Français uh, in um, in Europe, and there, you have to go to the front of the classroom and perform. And if you can't get it, then you get humiliated and sat down and stuff. I mean, Why is it that we tend to think of math as a solitary exercise to
Why?
be done at your desk or in a cubicle?
Why indeed. And, that was an experience that really changed me as a student. When I went to school, I had the same maths as we're talking about, where teachers just taught us methods and we went through these narrow exercise book questions. And I was pretty good at it, but I didn't think it was very interesting. I didn't plan to study maths. I thought I'd go into science. But then when I did A-level maths, which is what you do when you're 17, 18 in the UK, I had a teacher who just got us doing the problems together. And she said, here's a problem, talk about it in your group, think about how you'd approach it. And that just changed maths completely for me. It suddenly was a different subject that was about ideas, and we worked on it together, and it changed maths for me. It changed what I thought about myself. And yeah, so I've always known the power of having kids collaborate and connect with each other. The undergrad, I taught a class at Stanford a few years ago, calculus to about 100 incoming undergrads. And we decided to teach them to collaborate on calculus problems, but we gave them a test of collaboration. So when they came in, we put them in pairs and we said, we'd like you to solve these math problems together.
And remember, these are people from various levels, right? Some of them had already had
Yes, that's right.
exposure to the
Some had
topics, right?
taken calculus, some had never taken calculus. But so we gave them this math, and it was really of high school maths, but we said, solve these problems together. And we gave them different colored pens, and then we looked at their work. And so what most of them had done was draw a line down the center of the paper and just done their own thing on their own. And we taught them to do these calculus ideas in groups. And then at the end, we gave them another assessment, same thing, gave them different color pens. And we could see they were doing the work together. They were collaborating, they were connecting. And they talked about that was their biggest learning from the course, that they actually were working with each other's ideas and they had never done that before, which is pretty stunning, really. They came in thinking maths was this solitary competitive activity. So, yeah, I think it's really powerful. It's powerful for kids. Now, we have to teach teachers and students, and I do this work with my teachers, how to get kids to collaborate well. When you've got teenagers, you can't just put them in a group and say, do this together and expect them to do it well. But there are really good ways of having kids learn to collaborate well, and the good teachers use that.
But it's not just collaboration, it's also kind of lateral learning, right? So you talk about how, you need to present to your classmates and, take a skeptical attitude where it's like, wait, I need to know, wait, why does that make sense?
Yeah.
And I think it was, I forget who it was who said, if you can't explain it to your grandmother, then you probably don't understand it or
Yeah.
something like
Yeah.
that. What was
Well,
that?
if you can explain something, you're at a higher level of understanding. And so having kids explain is really good for their own understanding.
Well, you also talk about the visual tools, and so I think you talk about these Cuisenaire bars. And I remember, Montessori school, we had all sorts of these physical objects that we would use to learn math. And you also talk about the importance of drawing, right? Particularly, pen drawing, not like laptops and so forth. And and so, why is that? I mean, I think you said something to the effect that really, really good mathematicians, it's the visual cortex that is activated when they're solving problems.
That's right. I quote that research in the book. They've studied the brains of mathematicians and compared them with other academics. And the difference is they're using these visual pathways in the brain more often when they do maths. And we've been on our website, UCubed, we've been sharing visual maths problems for about 10 years now. And teachers, or all the teachers who use them, will just say how much more the kids were engaged and how it opens maths up. It's interesting, actually. I've been in classrooms where some groups are working on a number problem and some groups are working on the same problem that's visual. And in the number groups, the kids immediately start saying things like, I can't do this, or this is easy. Status differences come up straight away. When you make the problem visual, everybody's at the same space and they engage, they all share how they see it, and they have different conversations about what they see. So it's really not only is it important for our brains and learning in maths to see things visually, but it opens up maths to many more kids
Well, I think you also talk about how every problem has multiple potential solutions, right?
and ways of
And
doing it. Hmm.
yeah, now is this, I mean, the word diversity comes up quite a bit in the book. And I think it refers to a couple different things. But one way to think about it is that, there are these diverse ways of approaching a problem,
Yeah,
right? Rather than there being one correct
right.
pathway to
Right.
the solution. So, I mean, how important is it for instructors to kind of flesh these out or maybe even challenge students to, once they've come up with a solution, to come up with a different solution?
I think it's important. I think it helps kids, everyone see that you can solve problems in all these different ways and they're valued. So when I'm teaching, if somebody shares an approach to a problem, I will always say, did anybody see it differently? Or did anybody think about it differently? And then somebody else might talk about they did it, and there were two different ways to look at. And it brings kids in. I mean, one thing that holds students up in maths is thinking there's one way to do this. And I'm just trying to find what's in the teacher's head. So
Yeah.
when the teacher says, well, there are lots of ways to think about this, and I'd love to hear about the different ways you think about it, it again is really liberating for kids. I can't tell
Yeah,
you.
you had that one story where the kids, asked if they were following the rules, right?
Oh, yeah, that's what many kids think. Maths is all about rules. And in that particular classroom episode, the students were asked, they had a square with a quarter shaded in, and they were asked what fraction is shaded. It doesn't seem like a hard question. But a student goes up to the front and he says it's a quarter, or a fourth, as you say in the US, because um, that there's one part shaded, and that takes the area of, you could have four of them. It's one fourth, and he gives a good explanation for why it's a fourth. And one of the students says, "Well, what are the rules?" And the boy kind of falters at the front. He doesn't know what to say, and he's like, and the other boy follows up with, "Well, how do you know what to do if you don't know the rules?" So he's literally rejecting this kind of conceptual explanation that's made up of sense making, saying, "I can't engage. You need to give me a rule." So I feel so bad. This is the system of maths he's experienced. And they don't even see making sense of things as a valid thing to do in a maths classroom. So that's what happens when we teach maths, is just rules and procedures.
Yeah, I mean, it seems like people tend to learn better when they're thinking about these problems in less abstract ways, right? I mean, you have the example of, calculate the volume of a lemon. But I mean, I remember, when I would take a stats class, if it was just a pure stats class, it was kind of less interesting than, stats for business, stats for biology, stats for psychology, right? Where you had specific problems you're trying to solve.
And stats, I mean, really should be bringing in the world. There's no excuse for an abstract stats class. The And often kids find statistics and data much more interesting because of that, because you can ask questions of the world and use these mathematical tools to solve them and come up with different insights into how the world works.
Yeah, and I've talked to a lot of folks who are data scientists on my podcast, and I'm still kind of perplexed as to why we still teach trigonometry and calculus as opposed to data science in high schools. And I think you said this was something that was, I don't know, cooked up back in the 19th century, and there's just like a lot of institutional resistance. But it seems like it just makes so much more sense in today's world to be teaching data science and stats. So why don't we?
The UCs 5 years ago accepted data science as an alternative to Algebra 2. Kids could take data science and statistics maybe instead of going algebra, trig, calculus. And it was all going okay until actually one of your faculty at Berkeley heard about it and went on a campaign to have it shut down. And so they went and they petitioned the UC Boers committee, And the UC said, okay, no longer can kids take data science. Well, the argument's given, and this argument is a backwards argument, in my view. The argument is given that it is inequitable to offer kids a different pathway, and it will stop Black and brown kids doing well in life because it will pull them off the calculus pathway. And the calculus pathway is what is so important. So they share that argument. This is an inequitable set of affairs, offering kids data science, and people believe it. But actually, what data science was doing, what you see is when data science pathways are in high schools, they bring in a lot more kids who are more diverse, who haven't been traditionally successful. They take a course in data science and they start to see that maths can be really relevant, and they get really into it, and they go into STEM. So, it's frustrating to be in that situation.
Yeah, I mean, I get it, right? If you want to have a career in certain types of engineering, physics, and so forth, then it helps to know this stuff.
Right.
But you're probably going to take it again anyway when you get to
Yeah, I mean,
college,
that's the
right?
weird thing about calculus. 2/3 of kids who take calculus in the US high school system retake it in college or take a lower level course. So we have this kind of race to calculus in schools where kids are not understanding maths well because they're just trying to go fast to get to calculus. And then they end up redoing it in college anyway. So there's so many things wrong with the system. That push to calculus, though, and the filter of calculus, it's only taken by 16% of kids in the US. But parents are really behind wanting that calculus, that to be the filter. And so you get a opposition from parents if the school starts offering other courses, or maths is a harder system to change than others. I mean, the changes that people are trying to get in maths education is already the way other subjects are taught. Maths is the only subject that is taught in this way anyway.
Well, but I mean, if the 16% or only 16% are taking calculus, then what's wrong with letting the other 84% take data science, right?
I mean, nobody's saying take calculus away. They're saying have another option for kids. It's an interesting one. We could probably have a whole hour's conversation on the motives of the people trying to block change.
Well, I mean, it seems like some fundamental skills that everybody needs, not the people who are going to become, nuclear physicists, but the skills that everybody needs to be a productive member of society and a citizen include those three things you mentioned, right? Number sense, data literacy, and then relationships, linear and nonlinear. And I think having a broader understanding of those things would probably be more valuable to society than having this, relatively narrow procedural skill for a small percentage of people.
That's right. And, data science is really something all kids should be learning in school before they leave school, and be developing a data literacy and a comfort with data, and being able to read and analyze data to some extent is an important life skill. And it probably is really important to save our democracy, as a lot of misinformation is shared now. And if kids aren't leaving able to make sense of and separate fact from fiction, they will be left vulnerable to those misinformation campaigns. So, yeah, it's important just to be a everyday citizen.
Yeah, I mean, when I teach stats, I mean, I spend most of my time talking about mistakes, errors, misinterpretations, and all of that. And it seems like the best way to learn that is to actually make those mistakes.
Yeah.
So you talk about the importance of mistake making in the educational process. I mean, how do we bake that in? And why is it that we discourage it? I mean, I know you referenced the work of Carol Dweck quite a bit, right? And it does seem like growth mindset and having some comfort with dead ends is those things go together.
Yeah, they really do. And just the value. I mean, helping kids feel good about making mistakes and struggling, finding something difficult is really key to unlocking them and unlocking their learning of maths. So many students have the idea that mistakes are bad, and if you struggle, that means you don't have a maths brain. So it's only good the more we can do to make kids feel good, because it is an important part of learning, and you really won't do anything good in life without making mistakes. So um, we've had a lot of teachers really see that and talk differently to kids about mistakes, which is really good. Many of them, though, are working inside systems where kids are tested frequently and they literally get marked down for every mistake they make. So then it becomes hard to give those positive messages to kids when they're contradicted by the system.
Well, it seems like given the centrality of math education to education in general, the way in which we teach math has spillover effects into the rest of their lives, right? If this is how they learn that they're supposed to behave and they're supposed to avoid struggle, right? And avoid mistakes. I mean, that seems, I mean, even forgetting about math, that seems like, I don't know, a bad educational approach for kids.
Definitely. And I think the work of Carol Dweck and others is really important, that we need kids to have a growth mindset about their learning and their lives and their health. And that starts by making them feel comfortable in times of struggle and making mistakes, and realizing that perfection is not a good goal, that you really want to be comfortable with um, a more ish approach to knowledge. And yeah, that, as you say, it's important for everything in life.
Well, this term math-ish, I mean, it has a couple different interpretations, but one of them is this idea of, approximation, right? And understanding how to get a general sense of what an answer should look like. And, one of the things I say to my MBA students is that the important skill you're learning is when to zoom in, when to zoom out, right? Like how many decimal points do you really need to go to in any given situation? And if you're sending a, rover to the moon, well, maybe you need to be a little more precise than when you're forecasting next quarter's sales.
Right. Well, the idea of mathish is I estimation is really important. There's a lot of research evidence that we should be getting kids to estimate, and but I know that kids in schools hate to estimate, and they resist it, and they will work things out precisely and round them up to make them look like an estimate. But you ask them what's your ish number, and something magical happens, like they're willing to share their thinking. But it doesn't happen enough. One of the examples I give in Mathish is a question that was given out across the United States, which was, what's the closest answer to 7/8 plus 12/13? And the choices were 1, 2, 19, and 21. And so 7/8 and 12/13, both of those fractions are close to 1, and the good answer to that is 2 when you add them together. But the most given answer by 17-year-olds in the US was 19, and the second was 21. So people like hold their heads in their hands when they hear that, but I know those kids have never been asked to ish numbers, and it actually, if they'd been used to that, they would have easily got that question right. And actually, when you ask kids, well, what do you think it's going to be? What's your ish number? It gets them to kind of pull back outside of the procedures and think more conceptually. So it's a really good exercise. Also, with shapes and drawing or graphing, asking kids, well, what do you think that graph's going to look like, before they plot it and get in all the details? We'll have them thinking more conceptually about the ideas. So it turns out it's working really well in classrooms, and kids are very comfortable sharing their ish numbers. And it's freeing them to see maths a little bit less. It's less intimidating for them to share an ish number, and they are more willing to lean in and engage. So that's the idea of mathish.
Well, I mean, the other thing you highlight is the importance of converting difficult problems into simpler problems. And I mean, this seems to have applications well outside of math.
Indeed. Yes. Yes. And it's something successful maths people do. Like if you give a complex problem, they're very likely to make it into a simple problem to sort of see what's going on and apply that back. But when you ask kids, when you encourage that with kids, they have often had this such a fixed maths education that they don't think they can do that. They think if you've been asked this one question, you can't turn it into a different question. You have to answer that question. And we try and teach them that strategy, turn it into a simpler question. Like one example, I think I give in the book, a sort of complex maths question that's often used is, how many squares are in a chessboard? And the answer is not 64. So it's an 8x8 board, and you have 64 1x1 squares, but then you have these bigger squares. You have 2x2 squares and 3x3 squares. So that can be really complicated to work out, and you have to keep really careful track of your thinking. Somebody with a mathematical sort of way of working would say, well, let me try it first with a 4x4 board or a 2x2 board, and let me see what's happening as I make these squares. So yeah, you can use that principle in all of maths, really. If you're, I don't know, I'm just trying to think of one, ask something like 7/8 divided by 6/8. A lot of people would freak out with that question. But instead, you can just think of, well, what's 7/8 divided by 1/8? And then you have 6 of them. It's a much easier question. So yeah, that's one of the strategies that I teach my kids in the How to Learn Maths course.
Now, at some point in your career, you took an interest in neuroscience,
Mm-hmm.
right, and cognitive science. What does that tell us? I mean, it seems like whenever we learn about what's going on inside the brain, it lines up to some degree with our subjective experiences.
Yeah.
Are there any kind of insights that you can get from neuroscience that are just, aha, right? Um, aha moments for you
Yeah. I
that
mean, I
tell
think
you things?
one of the things that was really interesting to me in neuroscience, well, a couple actually. One was how making mistakes and struggling actually helps your brain. That's the time when your brain is strengthening and growing and connecting the most. That was kind of new knowledge for me. And then Vinod Menon's work, where he's mapped the brain as it works on maths and shown these 5 different brain pathways that are active. 2 of them are visual pathways at the back of the head, is really fascinating. And so that wasn't sort of common knowledge to me. And I think most people, they don't think their brain has this sort of interconnected pathways that are needing to be activated. So yeah, some really interesting insights, I think, from neuroscience. And brain plasticity, of course, was probably the biggest of all. When that came out, people did not think adults could change their brains. And in fact, the neuroscientists who shared the evidence of brain plasticity got a lot of pushback from the scientific community, saying it must be wrong. Now it's pretty well accepted, I think, that we have this brain plasticity, but not when it came out.
Well, you talk about how people, when they come to university with the intention of pursuing careers in STEM, there's a lot of attrition. A lot of people sort of, back out. Even ones that have been fairly successful in their math classes in high school. So, I mean, why is that? I mean, is it because they've been inadequately prepared to think in this way? Or is it because the people who are teaching in these topics, they also don't have a sense? I mean, when they're teaching physics and chemistry, they're also not understanding that those topics would benefit from a different approach to teaching.
And, as you said, most people who teach in universities have had no training in how to teach. And, well, one of the people I quoted, Mathish, was a very successful high school student, had multiple APs and did really well in the SATs and was going into engineering, but was so put off by the classes because they just were more memorization. And he thought coming to college, he'd finally be able to use his own ideas and think. And actually left the engineering program is in and went into psychology because there they actually did value his thinking. So I think a lot of kids have very bad experiences of intro math courses at universities. There's a few places that are doing a fantastic job and really welcoming kids into maths in college. But for a lot, I know that the first message they get when they get into their math classes is only a few of you are going to pass this class. The rest of you are not. And that's the first message the professors give them, which, you can only think about what that does to the students in the class. So we have a long way to go in university math teaching, improving that as well.
Well, if we're going to change the way math is taught, I mean, where does the change happen? Does it happen in education schools? And if you did teach people how to teach the math in this different way, would this be detrimental to their career, given that so many schools are required to have all this testing, whether the teacher
I
likes
don't
it or
think
not?
so, actually. I've had enough instances in my career now of people who have had one teacher who taught them to think conceptually and well about maths. And they talk about how much that changed them. My own undergrad students, we do maths conceptually, collaboratively, we solve problems. And so many of them say it's the only thing that kept me in my math classes afterwards at Stanford. And it doesn't hurt them that they then go into a lecture course with testing. It actually gives them different ways to approach the problems and think about them. But so no, I think it doesn't hurt people at all in any way. Where do we first change is a good question. Teachers in the K-12 system will tell me has to start in the universities because they're like the gatekeepers and it comes down to us from them. Like they were all excited to teach data science and then they were told by the UCs, shut it off. So they think the universities need to change. But I think many people in universities would say that there's K-12 schools need to change. Probably everybody does.
But it does seem like if you get exposed to this way of tackling problems and learning at some point in your life, then even if you go into an environment that is taught in a different way, you have the toolkit,
Right.
right,
That's right.
that
You have
enables you to
more
flourish.
tools you can use. And we have a summer camp program at UQ, just our research center at Stanford, where we bring kids in and we teach them over the summer in these ways. And I remember one of the students coming back to visit me at Stanford a couple of years later after the summer camp, and she said, in my school now, they don't let us use our own methods. We have to use the teacher's way. And we just have to use the teacher's method all the time. And I thought, that's really sad, not good. But at least she knows that there's other ways. And her way is a valid way of thinking about it. At least she has that to help her through that situation.
Right now, to getting back to this topic of diversity, I mean, it could be, I mean, one way to interpret mathish is that there are lots of different ways to teach math, lots of different ways to learn math. But I kind of got the sense that there is a preferred way, right? Which is the way you describe, right? It's better than the kind of
I
traditional
wouldn't
way.
say that it's preferred as much as, there's research backing for this. It's a scientifically backed approach to teaching and learning. I mean, it may be preferred as well, but it's not just that it's a preference. And the mathematical diversity idea really applies to the diverse ways people can think and approach maths. And that's an important piece of maths. That's what's most beautiful about maths to me, all the different ways you can see it and think about it and solve it. But many kids aren't experiencing that beauty because they're in the one way system. Do it my way and just follow the rules.
Is this approach more resource intensive, do you think? I mean, do you need to have, I guess, I don't know, smaller student to faculty
I don't think so.
ratios?
No. As a young elementary younger years elementary school teacher. Well, actually, I shouldn't say that. Any age teacher having manipulatives is good, particularly in those early years, but really all the way through, it's good to have actual physical mental models. But no, actually, if you teach kids to really work well with each other and collaborate, you can actually leave the room and not be the teacher there at all, and they will keep going and do this really important work. So I don't think it's harder to do in big classes. In fact, I use that approach in classes of 100, and the students become really self-sufficient and they are like teachers with each other. So yeah, I get that excuse from some teachers, I can't do that, my class is too big, and I don't buy that.
Well, there was one study you showed that you can actually teach the same content in less time,
Yeah,
right?
that's right. That was a really
And so you could presumably just,
yeah,
go around and divide the class up and spend time, right, instead of lecturing all the time,
right.
right? Just have these practice sessions.
Yeah, yeah. I mean, it's not about do we teach kids formal methods that people are teaching in lectures. It's really about how do they learn them, when do they learn them, and giving kids rich problems to work on and then sharing them methods while they're working inside these problems is a much more effective way of teaching them.
Well, what I found really puzzling about that study was that when the students were asked which method they thought was more effective, they 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 yeah. So why does it? So it seems like they think they're learning more when they're actually learning less, right? Why is that?
Actually, I give that study, that's one of the ones I give to my undergrads to read to get their perspective on it. Yeah, it was really interesting to study them with Harvard students where they really carefully contrasted different approaches, one of which kids were working on richer tasks and struggling, and the other they were in a lecture. But then each set of students switched over, so they each got both approaches. And the kids learned more in the active learning approach, where they were struggling and working on tasks, but they thought they were learning more in the lectures because it can seem really effective when you're sitting in a lecture and it's just told to you. But of course, it's not really until you try and use it that you ever know if you've really learned it. And often you don't in a lecture. So, but I think we have to help kids by not just engaging them in these different ways of working, but helping them know why they work and why they're important. And that was one of the conclusions of the authors of that study. We need to spend more time sharing with the students why it's good to struggle and why it's good to work in these different ways.
Now, look, some people say, right, if you can't measure it, then you can't change it. Um, what kinds of metrics could we potentially introduce to more accurately measure the learning process? If it's not this continuous testing, right? Is there a way that we can have a struggleometer or like a collaborationometer or a, compressionometer or, reference frame progress bar? I mean, how can we measure whether or not people are learning or
I
teaching?
think we need different assessments, and the assessments we have in the school system are very much things that are easy to test. Can kids repeat these methods? And especially in the age of AI, where AI can do those problems better than kids can or adults can. So I think we should be assessing kids' flexible, original, creative thinking. And you can do that. It's a different kind of assessment and not be giving them questions that a computer can answer for them. And that would help if we had an assessment system that valued this more conceptual creative thinking, then schools would pay more attention to that.
And so, how will AI change things? I mean, I remember when I was teaching finance, we originally would, you know, ban the finance calculators, and then we reluctantly allowed them, and then we banned Excel, and then we reluctantly allowed it, and now we're banning, ChatGPT, and then we're going to reluctantly allow it.
Yeah. I mean, that's what we should be doing is figuring out how can this help me in my learning and in my teaching. And that's what some amazing educators are doing. They're figuring out how can I make use of this in my teaching? And others are saying, oh, this is bad. We should ban it and not let students use it. So I would like the influence of AI to be that we no longer give kids these meaningless questions that they can just look up the answer to. Because if it's a question that ChatGPT can answer, then maybe it's not a good question. And that could up the game of mathematics education and the questions that are asked. But that would be I think, a good outcome of AI.
And how difficult would it be to modify the educational standards? Because, the public school system is very tightly tied to these
Yeah.
educational standards.
I mean, how difficult is it? It happens in some states easier than others. They have made good changes to standards in smaller states like Utah or Minnesota. Utah's made fantastic changes in maths. And when we try and make those changes in California, there are massive fights about it and pushback. And so I'm noticing this. It's not impossible. We're probably in the hardest state of all to get it to happen.
Well, look, if at K through 12, we maybe emphasize education over subject matter expertise. At the university level, we emphasize subject matter expertise over education. Do we need to maybe take all of our university instructors and, run them through some more training on how to teach? I mean, look, I know that teaching will never be the most important thing, right? Research will always be the most important thing. But as long as we have people teaching in universities, how do we get people with deep domain expertise to fall in love with understanding how domain expertise develops?
It's a good question. How do we get them to love it? I mean, I think our university instructors should get more training in teaching. And when they're coming in as beginning professors, most of them would welcome that, I think, to have some courses in how to teach. And I think once you know how to teach well and the ways you're teaching your courses and what I write about in the book, then people would get more interested in how kids think and learn. But if you're being taught content by somebody who doesn't care about teaching, who doesn't want to be there, that's not a good place to start.
But it is interesting that at every university, every major university, you have an education school. And as far as I don't know any faculty members at business schools, law schools, arts and sciences, med school that have ever sort of leaned on their education colleagues for insight. I mean, you'd think that given that we have all this expertise in-house, there would be more of a way
Yes.
to kind of
Yes, and the
spread the learning that
education
way.
school faculty would be very happy to work with the faculty in these other departments, but they never get asked. And sometimes it's worse than that. Sometimes they, like, the math department at Stanford don't like me. So it's not even neutral. It can become quite a difficult relationship. Now, some universities, they do have much better communication between education faculty and subjects. And in many places, actually, the mathematics education person is in the maths department and they work with professors. Tends to be more in state universities. The more elite the university, the less likely you see that.
Well, not only could you help them, but they could help you, right? Give you areas for, opportunities for field research,
Yeah, no,
right?
definitely. I mean, I see it as a two-way thing and it would be really productive. And that would be good if that started. There's more of that happening.
Well, Joe, thank you so much for joining me. This Mathish, along with your other books, are very inspirational for anyone who's interested in teaching, uh, particularly math, but not just math. Thanks so much.
Yeah, thank you for having me on the show. It's been a great conversation.
Unsiloed podcast is produced by University FM, elevating the stories of your institution.